building machine learning systems in the real world. It's it's quite a journey, isn't it? Starts maybe in a lab, a notebook somewhere, but getting it to actually work, deliver value outside that bubble. Well, it's incredibly
Oh,
complex.
absolutely. Think about standard software. You write code, it follows fixed rules,
Yeah.
right? Same input, same output every time. That's the expectation.
Right. Deterministic.
Exactly. But ML systems,
Mhm.
they're fundamentally different. They live and breathe data. And data, well, it's messy. It's always changing. It's noisy, sometimes incomplete. And that inherent sort of messiness makes these systems uniquely challenging from an engineering standpoint.
Yeah, precisely. It's not just about picking the right algorithm anymore. Suddenly you're facing all these practical engineering hurdles you just don't see with, predictable code.
Mhm.
So our goal today is really to unpack that whole journey. We want to look at the key stages, the core concepts you really need to get your head around to design, build, and importantly, operate these systems successfully out there in production.
Yeah, we'll basically follow the life cycle. Start with the absolute foundation, the data itself. Then we'll move through feature engineering, model development, and finally, those really critical steps of actually getting the system deployed and, crucially, keeping it running smoothly in the real world.
Okay, so let's kick things off with that bedrock data. I mean, it really is the most critical piece, right? You can have the fanciest model, but if the data's garbage.
You got it. Garbage in, garbage out still holds true, maybe even more so here. Success really hinges on data quality and just having enough relevant data. And that starts way back with understanding data engineering fundamentals.
Like what specifically?
Well, often you're dealing with all sorts of different data sources. Sometimes that means wrestling with, tricky tabular data. You might need a lot of effort just to pull together and join different signals that are scattered across various databases or systems.
And managing all the different formats too, JSON, CSV, Parquet, whatever it might be. And I imagine it gets even hairier when you start talking multimodal data, trying to combine images, text, maybe structured data.
Oh, definitely. The complexity ramps up fast. Then there's the whole infrastructure side of it, the storage engine itself, where you actually decide to keep your data. Is it a data warehouse, a data lake? That's not just some minor technical detail.
Right.
Making a poor choice there can create serious bottlenecks later on. It can
True.
really slow down how efficiently you can train your models.
And the way you process the data matters too, right? Batch versus stream.
Exactly.
Yeah.
You need to understand the difference. Batch processing, that's great for big tasks that aren't super time sensitive. Think like calculating complex features overnight or refreshing data labels once a day.
Okay.
Versus stream processing, which is essential when you need those real-time insights, for time-sensitive stuff.
Hmm.
Like imagine trying to spot credit card fraud. You need to
But
catch it now.
right, not tomorrow morning.
Precisely. You need that low latency, so stream processing is key there.
And tying a lot of this initial data work together is the ETL process: extract, transform, load.
Yeah, that's the classic workflow. Extracting data from all its sources, transforming it, that's the crucial cleaning, converting, maybe aggregating step, and then loading it into wherever you need it for analysis or training. You sometimes see ELT too, load then transform, but the principle is similar.
Got it. So once the basic data pipelines are flowing, then you face the challenge of preparing the specific training data for the model itself.
Exactly. Now you're thinking about things like sourcing and sampling. How do you actually select the data points you'll train on? Ideally, you'd use probability sampling for representativeness, but,
Yeah,
well, in practice,
it's often not feasible.
often not. You might end up using non-probability methods like convenience sampling, just using data that's easy to get, or snowball sampling, judgment sampling where an expert picks cases, maybe quota sampling.
Why go that route if it's less representative? Is it just
Mhm.
practicality?
Pretty much. It's often driven by cost, access, or maybe needing specific types of examples that pure random sampling wouldn't easily capture, like an expert using their judgment to find really tricky edge cases. The big caveat, though, is you lose that statistical guarantee of representativeness.
So you have to be super careful about potential biases creeping in.
Absolutely.
Mm.
You need to be really aware of how your sampling method might skew the data, and consequently how your model might perform or not perform on real-world data.
Okay. And then labeling. This feels like a huge, often underestimated part of the process.
Oh, it is. It's frequently the most expensive and time-consuming part of building a supervised ML system. I mean, the notes mention a Tesla engineer saying their labeling teams are basically as vital as their core engineering teams.
Wow, that really puts it in perspective.
It tells you something about the scale and importance, right?
So how do you even begin to tackle labeling, especially if you have like millions or billions of data points.
Yeah, it's a huge challenge. There are strategies, though. One is weak supervision. Here, you use heuristics, basically, noisy, programmatic rules or patterns you come up with, to automatically generate approximate labels for a ton of unlabeled data.
So like a fast but maybe not perfectly accurate labeler.
Exactly. The labels aren't perfect, they're weak, but they give the model a starting signal, something to learn from, especially when you have vast amounts of unlabeled data and only a little bit of the expensive hand-labeled stuff.
Okay, that makes sense. And then there's semi-supervision.
Right. Semi-supervision tries to leverage both worlds. You take a small amount of high-quality human-labeled data that you do have and combine it with a large pool of unlabeled data. There are different techniques, like self-training. Train a model on your labeled data. Use its most confident predictions to label some of the unlabeled data, add those pseudo-labels back in, and retrain.
Interesting. So the model helps label more data for itself.
Kind of, yeah. Or you might use cluster-based methods, making the assumption that data points sitting close together in some feature space probably share the same label.
And active learning, I saw that mentioned too. How does that fit in?
Active learning is another smart way to be more efficient with your precious labeling budget. Instead of just randomly picking data points for humans to label, the model itself flags the examples it's most uncertain about.
Ah, so it asks for help on the tricky ones.
Exactly. The idea is that getting human labels for these specific ambiguous examples gives the model the most bang for your buck, helping it learn faster and more effectively from fewer labels overall. It's really useful, especially if your data might be changing over time, helps the model adapt.
Okay, let's switch gears slightly to another really common data headache, class imbalance. What exactly is that, and why is it such a problem?
It's super common. It happens when you have a massive difference in the number of examples for your different classes. The classic example is medical diagnosis, like, say, detecting a rare disease. Maybe 99.9% of your data is healthy, and only 0.1% represents the actual disease.
So a naive model trained on that data could just always predict healthy and look incredibly accurate on paper, right? Like 99.9% accurate.
Precisely. But it would be completely useless because it would miss every single case of the disease. That's the danger.
Right.
The imbalance means the model gets very little signal, very few learning opportunities from that rare minority class. So it performs poorly where it actually matters most. Plus, you often have asymmetric error costs. Misclassifying a disease case as healthy is usually way worse than misclassifying a healthy case.
Definitely. So how do you combat that, assuming you can't just magically get more rare examples?
The absolute first and most important thing is to change how you measure success. Forget overall accuracy. It's misleading here. You have to use metrics that focus on the minority class performance and the trade-offs. Things like precision, recall, F1 score, maybe class-specific accuracy or AUC.
Recall seems key there, right? Finding all the positive cases.
Often, yes. Maximizing recall for the minority class is frequently the goal you want to find as many of the rare cases as possible, even if it means you get a few more false alarms, lower precision. It depends on the specific business problem, of course.
Okay, metrics first. What else? Can you change the data itself?
Yes, those are data-level methods. Resampling techniques. You can oversample the minority class, basically, duplicate existing examples, or, better yet, create synthetic examples using algorithms like SMOTE.
SMOTE. What's that do?
SMOTE stands for Synthetic Minority Oversampling Technique. Instead of just copying minority examples, it intelligently creates new synthetic data points by interpolating between existing nearby minority class examples. It gives the model more diverse examples of the rare class to learn from. The flip side is undersampling the majority class, just randomly removing some of the abundant examples. There are smarter ways, too, like dynamic sampling. The crucial thing, though, is you train on this balanced, resampled data, but you must evaluate your final model on the original imbalanced test set.
Right, to see how it performs in the real world it will actually face.
Exactly. You need that realistic evaluation.
Are there fixes you can make to the model or algorithm itself?
Yep. Algorithm-level methods. One common one is cost-sensitive learning. You essentially tell the learning algorithm, hey, misclassifying a minority example is 100 times worse than misclassifying a majority one. You assign different misclassification costs.
So the model's optimization directly considers the business cost.
Precisely. It adjusts its decision boundary accordingly. You can also use more advanced loss functions, like focal loss, which is designed specifically for dense object detection where imbalance is extreme. It automatically downweights the contribution of easy, well-classified majority examples during training, forcing the model to focus more on the hard-to-classify minority examples.
Interesting. And ensembles, do they help here?
Ensembles combining multiple models can sometimes help. By training different models, perhaps on different subsets of data or with different algorithms, the combined prediction might be better at capturing the nuances of the minority class. It's usually not their primary purpose, but it can be a beneficial side effect.
Okay. Another data gremlin, missing values. What are the main ways to deal with those?
Broadly, you have two choices. Deletion, just remove the rows, or sometimes even the entire feature column if it has too many missing values. Or imputation, fill in the missing values with some estimated value.
And which one you choose depends on why the data is missing.
Exactly. That's critical. You need to understand the type of missingness.
Yes.
Is it missing completely at random, MCAR? Like truly random. Maybe a sensor temporarily failed.
Okay.
Or is it missing at random, MAR? This is a bit subtle. It means the missingness is related to other variables you have observed, but not the missing value itself. Like maybe men are less likely to answer a certain survey question than women, but you know their gender.
Got it.
And the trickiest is missing not at random, MNAR. Here, the missingness is related to the value that's missing. Maybe people with very high incomes are less likely to report their income. If you just impute the average income here, you'll introduce significant bias.
Wow, yeah. That sounds like you really need to investigate. So imputation strategies depend heavily on that.
Absolutely. Simple mean or median imputation might be okay for MCR, maybe even MAR if you condition it properly. But for MNAR, you might need more sophisticated modeling techniques or even external information to impute reasonably. Or sometimes deletion is the safer option if you can afford to lose the data.
Makes sense. Okay, final data prep steps. Scaling and discretization. Why are these needed?
Right. Scaling numerical features is often crucial. Many ML algorithms, especially distance-based ones like KNN or algorithms using gradient descent like neural networks, are sensitive to the scale of input features. If one feature ranges from 0 to 1 million and another from 0 to 1, the first one can completely dominate the learning process.
Just because its numbers are bigger.
Exactly. Even if the second feature is actually more predictive. So you use techniques like min-max scaling, squashing values between 0 and 1, or z-score standardization, centering around mean 0 with standard deviation 1, to put all features on a comparable scale.
And discretization.
That's converting continuous numerical features into discrete categories or bins. Sometimes this can simplify the learning problem for certain types of models, like decision trees, or help capture nonlinear relationships.
Okay, phew. The data foundation is hopefully solid. Now cleaned, prepped, scaled, labeled. Now we move into what feels like more of the classic ML part, feature engineering.
Yeah, this is often where a lot of the magic happens. It's the art and science of selecting, transforming, or creating new input variables, the features that your model will actually learn from. And honestly, this is often where you get to the biggest bang for your buck in terms of performance improvement.
Really? More than picking a fancier model.
Often, yes. Even state-of-the-art models can perform poorly if they're fed weak features. Good feature engineering helps expose the underlying patterns in the data in a way the model can more easily pick up on. You're essentially injecting domain knowledge and intuition, guiding the model.
So it acts like a bridge between the kind of raw-ish prepared data and the model itself.
Exactly that. It comes after your initial data prep, but before you start training the model. And you're constantly thinking about how well these engineered features will generalize to new, unseen data. Selecting features that only work well on your training set leads to overfitting and poor performance in production.
Is feature engineering still important, even with, say, deep learning models that are supposed to learn features automatically?
Yes, definitely. While deep learning models can learn complex feature representations, providing them with well-engineered starting features can often significantly boost performance, especially if you don't have massive amounts of data. It can also make the model's behavior easier to understand and debug. You have features learned by the model and features you explicitly engineer.
What are some common techniques here? We touched on some during data prep.
Right, there's overlap because transforming data is creating features. So handling missing values, scaling, discretization, those are feature engineering steps too. Then there's encoding categorical data, turning text labels like city or product category into numbers the model can use. Common methods are one-hot encoding, label encoding, binary encoding. Each has pros and cons.
And feature crossing. That sounds powerful.
It can be. Feature crossing is creating new features by combining two or more existing features. This helps the model capture interaction effects. The classic example is combining, say, hour off day and day of week into a single Boolean feature like is rush hour.
Ah, because neither hour nor day alone fully captures that rush hour concept.
Exactly. The combination captures a specific interaction that might be highly predictive for something like traffic or ride-sharing demand.
It sounds like this requires a lot of creativity and domain knowledge.
It absolutely does. That's why subject matter experts, the people who really understand the problem domain, are invaluable collaborators here. They often have intuition about which signals or combinations are likely to be important.
How do you figure out which features are actually having the most impact?
That's key. You need ways to evaluate feature importance. Techniques like looking at coefficients in linear models, using tree-based methods like random forest or gradient boosting, which provide feature importance scores, or more advanced methods like SAP,
Basic.
Shapley additive explanations. It's a game theory-based approach that not only tells you which features are important overall, but also helps explain how each feature contributed to a specific individual prediction. It's great for interpretability.
Very cool. What about managing all these features, especially in larger teams? Seems like it could get messy.
Oh, it definitely can. Keeping track of definitions, ensuring consistent calculations, avoiding redundant work. This is where feature stores come into play. A feature store is basically a centralized repository or platform for managing the entire lifecycle of features. It helps teams define features, compute them consistently, store them, and serve them reliably for both model training and real-time inference. It's crucial for consistency and collaboration.
And speaking of consistency, what's the absolute biggest pitfall to watch out for during feature engineering?
Data leakage, hands down. It's insidious and can completely invalidate your model development process.
Okay, explain that. What is it?
Data leakage happens when your training data accidentally includes information that would not be available at the time you actually need to make a prediction in the real world. It leaks information for the future or the target variable into your features.
And the result is?
The result is your model looks fantastic during offline testing and validation because it's effectively cheating. It's using information it won't have access to later. Then when you deploy it, its performance collapses because that leaked information isn't there anymore.
Can you give a simple example?
Sure. Predicting customer churn. If one of your features is, say, reason customer left service, well, you only know that after they've already churned. Using it to predict churn before it happens is leakage. Or maybe calculating an average user spending feature, but accidentally including the transaction you're trying to predict in that average. It requires constant vigilance.
Yikes. That sounds easy to do by mistake. And I guess this whole feature process is never really finished.
Pretty much. The notes emphasize it's iterative. You build a model, you analyze its errors, you go back, you tweak features, create new ones based on what you learned, retrain. It's a cycle. Never done with data and features.
Okay, so we've battled through data prep, crafted some hopefully powerful features. Now we get to model development and evaluation. Choosing the model, training it, seeing how good it is. What's the first principle here?
Start simple. Seriously, resist the temptation to immediately jump to the most complex, state-of-the-art model you read about last week.
But why? Isn't the goal the best possible performance?
Yes, eventually. But starting simple gives you a crucial baseline. It helps you validate your entire pipeline. Is the problem framed correctly? Is the data flowing as expected? Are the features actually helping? Simple models are way easier to implement, deploy, debug, and critically to interpret.
Okay.
Getting a simple baseline model into production, even if its performance isn't amazing yet, lets you test the end-to-end prediction infrastructure and ensure it's consistent with your training setup. That consistency check is vital before you invest in more complex models.
So you only ramp up complexity once the simple baseline plateaus, and if the problem really needs more predictive power.
Exactly. Then model selection becomes about choosing from a suitable set of candidates based on your task. Is it classification, regression, something else? How much data do you have? What metrics matter most? And always understanding the trade-offs, complexity versus interpretability, training time, prediction latency, maintenance cost.
And checking if your data actually fits the model's assumptions.
Crucial step. Many models make assumptions about the data, like linear classifiers, assuming a linear decision boundary, or some statistical methods assuming normality. If your data violates those assumptions, the model might not perform well no matter how much you tune it. You need to understand the tool you're picking up.
Makes sense. So you train a model. How do you actually know if it's any good? Yeah. Evaluation time.
Right. And evaluation isn't just about getting a single score. It's about understanding the model's quality, ensuring it aligns with the actual business goals, and comparing different models or versions. But a raw metric like 90% accuracy means almost nothing in isolation.
You need a baseline to compare against.
Absolutely. You must compare your model's performance against something meaningful.
Yeah.
Is it better than random guessing? Is it better than a simple rule of thumb heuristic? Is it better than just predicting the most common outcome, the zero rule baseline? Is it better than current human performance or the system it's replacing? Without that context, the metric is just a number.
And we already talked about looking beyond overall accuracy, especially with imbalanced data. What else should evaluation cover?
Definitely need to assess robustness. How does the model handle noisy or slightly perturbed inputs? The notes had that great example of a cough detection model trained on clean lab data, feeling miserably on real-world noisy recordings.
Right.
So you need perturbation tests. In variance tests, does changing an unrelated input affect a specific output? Directional expectation tests, if I increase input X, does output Y change in the expected direction? These help build confidence that the model isn't just brittle or learning spurious correlations.
What else?
Fairness is huge. Evaluating performance across different slices or subgroups of your data is critical to uncover potential biases. Is the model performing equally well for different demographics, for example? Calibration is another key aspect.
Calibration? You mean if the model says it's 90% confident, is it actually correct 90% of the time?
Exactly that. A miscalibrated model, even if it's generally accurate, can be misleading and erode user trust. If it's constantly overconfident or underconfident, its scores aren't reliable for decision-making. You also want to measure confidence generally. And just basic sense-making. Do the predictions seem plausible in the real world?
And analyzing the mistakes the model does make.
Super important. Digging into the specific errors. Where is the model going wrong? Are there patterns? This is often your best source of ideas for creating new features or identifying data quality issues. And documenting all this evaluation, the metrics, the slices, the tests, the limitations, is where things like model cards become really valuable for transparency and responsible development.
How does the model actually learn during training? That involves the objective function or loss function, right?
Yes, the loss function is essentially the guide for the learning process. It quantifies how far off the model's predictions are from the actual ground truth values. The goal of training is typically to find the model parameters that minimize this loss function.
And different tasks need different loss functions.
Right. You'd use something like mean squared error, MSE, for regression problems, where you're predicting a continuous value, and something like cross-entropy loss for classification problems. The key takeaway here is making sure your chosen ML objective function aligns as closely as possible with your actual business objective.
How so?
Well, sometimes optimizing purely for, say, AUC or accuracy doesn't actually lead to the best real-world outcome. You need to consider the utilitarian performance. How are these predictions actually going to be used, and what's the downstream impact? If optimizing a slightly different metric leads to better business decisions, that might be preferable, even if the raw predictive score is a tiny bit lower.
Interesting trade-off. Any advanced modeling techniques worth mentioning briefly?
Ensembles are pretty common and effective. The idea is to combine predictions from multiple individual models or base learners. This often leads to better overall performance, increased accuracy, and more robustness. It helps reduce overfitting by averaging out the errors or biases of individual models.
How do you combine them?
Techniques like bagging, like random forests, boosting, like gradient boosting machines, or stacking, training a meta model on the predictions of base models. Even simple averaging or voting of predictions can work well. The advice generally is to keep ensembles reasonably simple if possible.
And AutoML, where does that fit?
AutoML, or automated machine learning, aims to automate various parts of the ML pipeline, especially the tedious bits like model selection and hyperparameter tuning. It can potentially speed up development significantly and maybe make ML more accessible to folks who aren't deep experts.
So it picks the model and tunes it for you.
Sort of, yeah. There are sophisticated techniques like neural architecture search, NS, which is sometimes called hard AutoML, that even try to automatically design the optimal neural network structure itself. The catch, as the notes point out, is that really advanced AutoML can be incredibly computationally expensive and complex to set up, often limiting its practical use to companies with huge resources.
Right. Okay, so we've engineered features, trained a model, evaluated it carefully. Now for the really scary part, deployment and operation. Getting it out into the wild and keeping it alive.
Yeah, this is where many projects stumble. It's about getting your trained model ready to actually make predictions on new data. First, you need a prediction strategy. Will it be online prediction?
Meaning real-time, low latency.
Exactly, like recommending your related product the instant a user clicks on something. Or will it be batch prediction, Processing data in chunks, maybe overnight, like generating a daily sales forecast or scoring leads for the next day. Hybrid approaches are common too, and real-time ML is definitely a growing trend.
And supporting all this requires solid infrastructure. This is where MLOps really comes in.
Absolutely non-negotiable for production ML. MLOps provides the tools, practices, and culture for building, deploying, and maintaining ML systems reliably and scalably. It covers everything from storage and compute resources, consistent development environments, version control for data and models.
.CI/CD pipelines for automated testing and deployment of ML models, orchestration tools like Argo or Kubeflow pipelines to manage complex workflows.
Right. And containerization tech like Docker is almost essential for packaging your model, its code, and all its dependencies into a reproducible unit that can run consistently anywhere.
What's one of the biggest, sneakiest problems that can bite you once you deploy?
Training serving skew. That's a huge one. It's when the performance of your model in production is significantly worse than what you saw during offline evaluation, and it's often due to subtle differences between your training environment and your live serving environment.
So the data the model sees when making predictions is somehow different from the data it was trained on.
Exactly. It could be differences in how features are calculated, maybe a bug in the serving code that wasn't in the training code, or differences in the data itself. Maybe the serving system pulls data from a slightly different or less fresh source, or data distribution simply drifting over time.
How do you even detect that, let alone fix it?
The rules of ML from Google actually have specific advice here. Rule #29 is about logging the features used by your live prediction service and feeding that data back into your training pipeline for comparison and monitoring. Rule #32 emphasizes reusing the exact same code for feature generation in both training and serving whenever possible.
Minimizes the chance of discrepancies creeping in.
Right. And testing your model on future data collected after your training set cutoff before deploying, is also a good practice to simulate the production environment more realistically.
And you really need to test the model in production too, right? Not just rely on offline tests.
Oh, absolutely. Offline evaluation is necessary but not sufficient. Techniques like shadow deployment are crucial.
How does that work?
You deploy your new model alongside the existing production model. Live traffic goes to both, but only the old model's predictions are actually used by the downstream system or shown to users. You closely monitor the new model's predictions, performance metrics, and operational health in the real environment, comparing it to the old one.
So it's like a final dress rehearsal with live ammo, but without impacting users.
Exactly. It's a key part of ensuring a safe rollout and often part of a continual learning process. A good production checklist usually includes things like running in shadow mode for a certain period, like 48 hours, having an immediate fallback mechanism, and doing proper load testing.
What if your amazing model is just too big or slow to serve efficiently?
Then you need to look into model optimization techniques. Things like quantization, reducing the numerical precision of the model's weights, say from 32-bit floats to 8-bit integers, or model compression using techniques like low-rank factorization or knowledge distillation.
Knowledge distillation.
That's where you train a smaller, faster student model to mimic the output distribution of a larger, more complex teacher model. Or pruning, removing redundant or unimportant weights or connections within a neural network, all aimed at making the model smaller, faster, and less resource-intensive for serving.
Okay, it's deployed, optimized, now you just let it run, right?
If only. Now the real work of monitoring and maintenance begins. And this is continuous. ML systems need monitoring that goes way beyond traditional software monitoring.
Right.
Because their performance is fundamentally tied to the data they see. And data drifts, changes, degrades. It's not enough to know if the prediction service is up and running. You need to know if the model is still actually making good predictions.
So monitoring catches those silent failures, where performance just gradually decays without any obvious errors.
Exactly. It helps detect that slow degradation. It also catches upstream data issues. Maybe a data table your model relies on suddenly becomes stale or gets corrupted. And of course, monitoring tracks standard operational metrics like uptime, request latency, especially tail latencies like P95 or P99.
But also critical ML-specific performance metrics like accuracy, precision, recall, F1 score, maybe AUC, continuously tracked over time.
Yes, and crucially, linking those back to the actual business metrics the model is supposed to influence.
And monitoring for data distribution shifts seems absolutely vital.
It's probably the most critical ML-specific monitoring task.
Right.
Because shifts in the input data distribution are the most common reason models degrade in production. You need to watch for different types of shift. Like a covariate shift. The distribution of your input features, the X's, changes. Maybe your user demographics change over time. Labels shift. The distribution of the target variable, the Y, changes. Maybe overall purchase rates go up seasonally. And concept shift. The underlying relationship between inputs and outputs changes. Maybe user preferences change, so the same user profile is now less likely to click on a certain type of ad.
How do you actually detect these shifts automatically?
There are various techniques. Statistical tests comparing distributions of features between a reference window, like your training data, and the current live data. Things like Kolmogorov-Smirnov tests, Population Stability Index, PSI. For high-dimensional data like images or text embeddings, you might use embedding-based drift detectors. And just basic tracking of feature distributions over time using histograms is fundamental.
Are there tools for this?
Yeah, standard monitoring tools like Prometheus and Grafana can be used for basic metric tracking. And there are also specialized open-source libraries and platforms like Evidently AI, YLabs, Arise AI, Fiddler AI that focus specifically on ML monitoring, drift detection, and explainability in production.
How does observability relate to monitoring?
Observability is a broader concept. Monitoring tells you if something is wrong. Observability helps you understand why. For ML, it means having deeper insights into the entire system, including the model's internal state and behavior interpretability plays a big role here. It's about being able to ask arbitrary questions about your system and get answers, which is crucial for effective debugging. It's really a design principle.
And ensuring the data entering the system is still valid, like data quality checks.
Yes. That's often called feature validation or data validation. Think of it like automated unit tests for your data pipelines. Tools like Great Expectations or Deek allow you to define assertions or constraints about your data. Things like, this column should always be positive. This categorical feature should only contain these allowed values. Missing values shouldn't exceed 5%.
So it catches bad data before it messes up the model.
Ideally, yes. Garbage in, garbage out, validating the input data quality is crucial.
Okay, so monitoring detects problems like drift or degradation, then continual learning is how you actively fix those problems.
Exactly. Monitoring is the passive detection system. Continual learning, or continuous training CT, is the active response mechanism. It's about systematically updating your models over time using fresh data to adapt to those detected shifts and maintain performance as the world changes.
How are models typically updated? Just retrain from scratch periodically.
That's one common approach. Periodic, full retraining. You gather the latest data, train a completely new model, stateless retraining, evaluate it, and deploy it, replacing the old one. The frequency, daily, weekly, monthly, depends on how fast your data drifts and how valuable freshness is.
What's the alternative?
Incremental updates, or online learning, stateful training. Here you take your existing model and fine-tune it using only the newest batch of data. This can be much faster and more computationally efficient, especially if you have streaming data. However, it can sometimes be less stable or lead to catastrophic forgetting, or the model forgets older patterns. Honestly, a lot of continual learning boils down to an infrastructure challenge. You need robust, automated pipelines that can handle these frequent updates, whether they're full retrains or incremental ones. Think reliable data access, managing labeling latency, especially for labels that take time to appear naturally. Efficient evaluation bottlenecks, you need to quickly validate every update, and choosing algorithms that actually support efficient updating.
And you still need to test those updates carefully in production.
Absolutely. Every retrained or updated model needs to be validated before going live, often using those test and production techniques like shadow deployment or A/B testing to confirm it's actually an improvement and isn't causing unexpected harm.
Wow. Okay, so beyond all these deeply technical components, the data, the features, the models, deployment, monitoring, updates, we also need to remember the bigger picture. The infrastructure, the MLOps practices tying it together, and the human element.
Right. That MLOps infrastructure and tooling layer really is the bedrock that enables everything else we've talked about. Storage, compute, dev environments, versioning, CI/CD, orchestration, maybe a full ML platform.
Yeah.
It provides the scaffolding needed to manage this complexity in production.
And the human side, who's involved there?
It's a whole ecosystem. Data scientists, ML engineers, data engineers, software engineers, operations folks, product managers, business leaders, the actual end users interacting with the system, and even broader society potentially impacted by its decisions.
And one of the most critical human-centric steps happens right at the beginning, problem framing.
Absolutely fundamental. Taking a fuzzy, real-world business need and translating it into a concrete, solvable ML task. This requires deep collaboration and understanding. What's the actual business goal? Who are the users? What are their needs? How will the ML system fit into the existing workflow?
Because success isn't just a high accuracy score.
Exactly. Success is defined by whether the system actually moves the needle on key business metrics. How you frame the problem dictates the data you need, the model you choose, the metrics you optimize, the system architecture, and ultimately, how difficult the whole thing will be. It often involves balancing conflicting goals from different stakeholders and doing a serious cost-benefit analysis. Sometimes the best solution isn't ML at all.
And the user experience of interacting with an ML system needs thought, too.
Definitely. Users are accustomed to deterministic software. The probabilistic nature of ML being mostly right but sometimes weirdly wrong, or maybe having higher latency than users expect, can impact usability and trust. Designing the user interface and feedback loops carefully is important.
Finally, responsible AI. This feels like it needs to be woven through the whole process.
It absolutely should be, not an afterthought. Thinking about fairness, interpretability, accountability, transparency, privacy, security, these ethical considerations need to be embedded throughout the life cycle. Are we building systems that are fair across different groups? Can we explain critical decisions when needed? Are we transparent about the system's capabilities and limitations?
Model cards help with that transparency.
They're a good step, yes. Documenting the model's training data, evaluation results, including performance on different subgroups, intended use cases, known limitations, and ethical considerations helps promote transparency and accountability. It's all part of building trustworthy AI systems that benefit users and society.
Whew. Okay, pulling all that together, it really hammers home that building ML for the real world is.
Well, it's a whole different beast compared to just training a model in a notebook. It really is.
Yeah?
It's this complex dance between data engineering, thoughtful feature engineering, careful model development, robust deployment, vigilant monitoring, and continuous adaptation. And yet, data is absolutely foundational. Good data and feature practices are paramount.
And it's clearly not a one-and-done thing. It's deeply iterative. You're constantly learning from how the system behaves in production, feeding that back into refinement and updates. It's never truly finished.
That's a great way to put it. And success hinges not just on technical chops, but just as much on deeply understanding the business problem, collaborating effectively across different teams and roles, and always considering the human impact and ethical dimensions.